My name is Lucas, and this complex analysis course follows the textbook by Dennis Zill. And let's get started. 1.1. Complex numbers. And their properties. So first, let's start with a definition. Complex number. A complex number is any number of the form z equals to a plus ib, where a and b are real numbers and I is the imaginary unit. And let's start with another definition. The notation a plus ib is the complex number and the real part of z, denoted by capital R-E of z. It is a, right? So this is the real part of z, right? And the imaginary part, the imaginary part of z, denoted by im z is equal to b, which is b, right? B is also a real number, and let's say another definition. I'm just copying the textbook. That's how I learn. A real constant multiple of the imaginary unit is called a pure imaginary number. Well, let's do an example. Right. Let's say z is equal to 4 minus 9i, then the real part of z, the real part of z, it's 4, and the imaginary part of z, it's -9. And let's say well, now let's give an example of a pure imaginary number. Well, that is z is equal to 6i, and this is pure imaginary number. The real part of z is equal to 0. Think of it as 0 plus 6i, right? And the imaginary part of z is 6, right? And now, definition. Equality. Complex numbers. z1 equals to a1 plus b1i, or just you can flip it around if you wish. That's how I read it, but the textbook read a different way. They wrote I first. That's okay. z2 is equal to a2 plus b2i, right, are equal. That is z1 equals to z2 if a1 is equal to a2. So I will use a discrete mathematics symbol over here, and, right, and b1 equals to b2. Now, let's do another definition. The totality of complex numbers, yes, complex numbers, or the set of complex numbers is usually denoted by C, right? C. But this is how I write it. Because this is a capital letter, we usually write it like this, right? This is not in the textbook, but that's how I write it, right? I write my remarks, my personal remarks, in blue. That's how I do it. That's my format, right? And because any real number, A, can be written as z equals to a plus 0i a plus 0i, we say that the set of real numbers is a subset of C, right? Let's give another example, right? Let's say 3, right? 3 is an element of real number, right? And 3 is equal to 3 plus 0i. equal to z, and 3 plus 0I is in fact a number of the set of complex numbers, right? And as for the notation, maybe we can write it as, over here, this is my own remark, right? This is equal to the subset of C, right? This is how you write it in group theory, right? Just think of it as like a bigger sign. We know C is bigger than R, right? No, sorry. Maybe this, because because R can never be equal to C. There's always more elements in C than R. Okay, now let's move on. So there are some properties or arithmetic operations. So that is a theorem, right? Arithmetic operations. Complex numbers can be added, subtracted, multiplied, and divided. And if z1 is equal to a1 plus b1i, z2 is equal to a2 plus b2i, then the operations are defined as follows. Well, we have addition. z1 plus z2, or that is equal to, if we would expand it, right? a2 plus b2i, right? Well, how about we combine like terms, right? And the real part, it's a, right? That's a1 plus a2, right? If we factor out the I, right? Well, we can write it in front this time. That is b1 plus b2, right? So this is how addition is defined. And subtraction, that is z1 minus z2, and that is equal to, if we expand it and we, a2 plus b2i, right? Sorry, this is minus, right? This is how I change it. This is a minus sign, sorry. Well, this is equal to, well, we combine like terms, right? This is a2 minus a1 minus a2, right? And we want to add I, right? And then we still have the negative sign over here, b1 minus b2, right? And multiplication. That is equal to a1 multiplied by a2 is equal to a1 plus b1i multiplied by a2 plus b2i. Or if you actually do the product and you combine like terms, right? You will get a1, you get a1, a2 minus b1, b2, right? And then you add the imaginary part, that is a1, a2, that's a1, b2, right? That is basically the residuals in the middle when you do the multiplications. Right. You can really multiply out. Really, you can set up a square. And you can really do just a1 plus b1i, and then you a2 plus that's b2i, and then you multiply this, right? And then you get that's a1 b2 I and I goes together, makes a negative sign, right? Very well. And now let's define division, right? Division, that is z1 over z2, that is equal to a plus b, a1 b1i, a2 plus b2i. Well, you know the real part cannot be 0 because or else this is not defined, right? Well, basically that is z1 does not equal to 0, that is does not equal to 0 plus 0i, right? Really, that's what it meant. Well, the corollary to this is that a2 does not equal to 0, b2 does not equal to 0. There. And it's or because, well, either one of them are 0, it's okay, right? Really. No, sorry, or is this symbol. That's or, right? And that is equal to a1 a2 plus b1 b2, that is the real part, and you have a2 square plus b2 square and plus I, that's the imaginary part, a1 a2 minus a1 b2 that is a2 square plus b2 square, right? This, I don't know if this can be written in like determinate. This is b, this is a1. So this is how I learn. I always try to make some assumptions and try to prove it, right? So this is b2. Try to simplify things, right? That's a1 and b2. That's a1 and b2, right? And this is this, right? And you have b1 a2. So it's negative determinant basically. You can rewrite the top as the negative determinant. Yeah, das ist gut. Die mache ich. Okay. And well, we have commutative laws, right? Just like linear algebra. Yeah. They always teach these things. Oh, sorry, not complex. Commutative laws. That is, well, you have a1 z1 plus z2, that's equal to, well, z2 plus z1, right? You also have the multiplications, right? You have a z1 z2, that's equal to z2 z1, right? And you have associative laws, right? A property actually, but they write it as laws. I always say property, associative property. Laws. That is, well, z1 plus, well, if you add z2 and z3 together, that's equal to if you add z1 and z2 together first, and then you add z3, and same as multiplication, right? z1, z2, z3. Just a side note, we say Gauss invented complex numbers or imaginary numbers. Really, that's just a side note, and distributive property, right? Distributive property. Oh, sorry, law. That's how they write it in textbook. Law. Well, that is Z1 if you have a sum over here inside a bracket. Well, that is equal to if you would distribute it. And they're commutative, you can flip it around, it's okay. Perhaps you can write like this. This is not from the textbook. This is my courtesy. I wrote over here, right? Now, let's say theorem. Addition, subtraction, multiplication. So, first, to add or subtract two complex numbers, simply add or subtract the corresponding real and imaginary parts. Second, to multiply two complex numbers use the distributive law and the fact that I square is equal to -1, right? And now let's do another example. I think we do have enough space, so that is example 4, right? Example 4, right? If Z1 is equal to 2 plus 4i, Z2 is equal to Z2, it's equal to -3 plus 8i. Well, first we want to calculate Z1 plus Z2, right? That's part A, but there's no point of me copying it twice, right? So that is equal to 2 plus 4i plus -3 plus 8i. It's equal to 2 minus 3 plus 4 plus 8i. That's equal to -1 plus 12i. And let's do part 2. Part B. Part B is we multiply Z1 and Z2. We wanna find that, right? And well, yeah. It's always better to have a textbook and take notes with me. Really, that is equal to 2 plus 4i, and that is -3 plus 8i, right? And that is equal to, well, 2 plus 4i. That is equal to 2 plus 4i. Well, and if we distribute these two, right? This is -3, and this is 8i, right? That is equal to, well, -6 minus 12i plus 16i, and plus 32i squared. Well, that's -1, really. But yeah, you can combine it. -2 minus 32, right? These two numbers. That is the real part. And now let's combine the imaginary part. That is sorry, it's too messy. Minus 12i, right? That is equal to -38 plus 4i. So there we are done. Right. I think we can move on to the next page. Sorry, my writing, my script is execrable. Well, that is not a characteristic of a teacher, but well, I hope you can bear with it, and I think just doing examples with me is really helpful. And now we start with another definition. That is 0 and unity, right? So the 0 of complex numbers, I paraphrase a little bit, it's this complex number system, but 0 of the complex number is the number is the number 0 plus 0i, right? And the unity is 1 plus 0i. There. And the 0, fine, I'll just copy it. The 0 and unity are denoted 0 and 1. Really, this is trivial, respectively. The 0 is the additive identity zero is the additive identity in the complex number system. Since for any complex number 0 plus, well, z is equal to a plus ib, we have z plus 0 is equal to z. Right. Really, this is very trivial. Maybe we don't need to copy that. Really, if you can read my handwriting, just copy my notes. I know my handwriting is really messy, but that is that. Well, let's prove it, right? If z is equal to a plus bi, then, right, we see that z plus 0 is equal to z, right? A little proof, right? A plus bi, so this is proof. I usually add it over here, but I think we don't need a long proof. That is, well, 0 plus 0i, right? That is z plus 0, well, that is equal to a plus 0 plus I b plus 0, that's just a plus b, I, that's equal to z. So proof is complete. And now next, we have the unity. The unity is the multiplicative identity that is. Well, I'm just skipping a lot of the verbiage. It's really not necessary, right? Well, let's do another proof. That's how I take notes, really. I don't copy everything. Only copy the important ones, right? That is z times 1, that is equal to, you see z times 1 plus 0i, that is equal to z, right? Proof is complete. And now we have a theorem. Well, I will post my notes, I hope. Really, I don't know. I might. It depends on this website. No, this application that I use. Right. So now, theorem conjugate. Well, if z is a complex number, the number obtained by changing the sign of the imaginary part of z is called the complex conjugate. Or simply conjugate. And denoted by that is, if z is equal to a plus bi, then z is equal to a minus bi. There. Now let's do some examples. That's example 4. Let's do example 5. Right. So well, let's actually do some examples. So z, and then we can get into general case. That's how I teach, really. So if this is z is defined in this manner, then z conjugate is equal to 6 minus 3i, right? And let's say if z is equal to negative 5 minus I, right? And then z conjugate is equal to negative 5 plus I, right? And let's say z is equal to 7, right? Then z conjugate is equal to 7, well, really just plus 0 minus 0i, it's just the same thing. So now we may propose this this hypothesis. So I wrote theorem. This is my own theorem, right? But it's written in a textbook, really. They didn't highlight it, but this is how I take notes, really. You have to accentuate what is important, right? So some properties, right? Properties of conjugates, right? So first you have, well, z1 plus z2. Well, that is just equal to z1 plus z2, but with conjugate, right? And, well, what if it's negative sign, right? that is, well, that is this, the conjugate of z1 minus z2. Well, that is if you can, that is if you distribute the conjugate sign, right? And we can do some proofs later, right? And z1 z2, right, that is equal to z1 z2. That's if we distribute the conjugate. And now if we have a conjugate of a fraction, right, that is equal to if we distribute the conjugates. Very straightforward. And well, so now let's do some examples, right? Just proving some extra theorems, extra properties, right? So what if you get this, right? So this is one of the properties. I do it as a practice problem, right? So you have a plus bi, right? You have plus a minus bi, that's conjugate, or that is just equal to a plus imaginary part, that is b minus b, that is equal to 2a plus 0, that is equal to 2a, right? This is one of the properties, right? And then you, let's say, z minus the conjugate of z, right? That is equal to, well, a plus bi, a minus bi, that is equal to, well, a square minus a, that's just a product, right? The middle terms cancel, right? And I squared is equal to -1, that is equal to a squared plus b squared, right? And let's say you have z minus the conjugate, that is equal to a plus bi minus a minus bi, that is equal to a minus a, that is plus b, that's bi, right? And then plus becomes, well, minus becomes plus, right? That is equal to plus bi. Well, a and a cancels out, that's 0, and then you factor out the I, right? That is b plus b, that is equal to 2bi, right? And, well, let's see, let's find the real part of a plus, well, let's find the real part of y for this one, right? Well, of real part of real part, that is equal to minus z plus, that is z plus z conjugate plus, well, divide by 2, right? And then that's imaginary part of z, that is equal to z minus z, the conjugate of z, and divide by 2i, right? Now let's propose another theorem. Division. To divide z1 and z2, will you multiply by the denominator? Will you multiply the numerator of z2 that by the conjugate of z2? Really? There. Well, that is really, I don't understand why is this a theorem. Okay, there. So multiply by the conjugate of z2, right? That is equal to, well, z1, z2, that is equal to z2 conjugate of 2, z2, right? And then use the fact that, and then z2 is equal to is the sum of the squares. Really, the textbook is very verbose. Real and imaginary parts of z2, right? Do you have any more space? We do. Well, let's do an example, right? This is example 7. In textbook, it's example 2. They don't give as much examples as I do, or it's just that they understated it. Okay. Anyways, so if z1 is equal to 2 minus 3i, z2 is equal to 4 plus 6i, well, find, really, I'll just use my notation. So z1, it says find z1 divided by z2, so I'll write it like this. Okay. Really, you have to know how to take notes. Okay, well, let's do it. Let's write over here. Right. z1 divided by z2 is equal to negative I, and then you have 4 plus 6i, right? That is just z1 and z2, and well, how about we multiply by the conjugates, right? Minus 6i, right? And just by a difference of square, right? So this is equal to 4 squared, that's 16, and you have 6 squared, that is 32. No, it's 36, sorry. And you have this, right? No, I did it correctly. Yes. Plus 18i squared, right? That is equal to, well, if you combine like terms, you see you have 24i now, right? So that's negative 10 minus 24 I divided by 52, right? There. And because we want the form in terms of a plus bi, right? Right. We want it to be, a plus bi, right? Well, that is, well, then our answer, it is equal to, well, negative 10 divided by 52. Really, that is just 5 divided by 26. That's 5 over 26. Well, that is also equal to space. Oh, there. Minus 5 divided by 26 minus 6 over 13. There. That's example 7. And now we propose another theorem. Like this. Theorem inverses every number z has a unique additive inverse. Right, and or that is well, if z is equal to a plus ib, right, then the additive inverse is equal to negative z. That is equal to negative a minus ib, right? Because z minus z is equal to 0. There. The textbook wrote a paragraph about this. Really, there's a multiplicative inverse, right? So any complex number possesses a multiplicative inverse so for z does not equal to 0, then well then only one non-zero complex number z inverse such that z multiplied by the inverse is equal to 1, and z inverse is also called the reciprocal right of z, so just reciprocal, right, 1 over z. There. Example 8. So you have z is equal to 2 minus 3i, right? And well, let's find the reciprocal of z, right? Okay, so this is z, right? And well, we don't want imaginary numbers on the bottom. That is more of a convention, right? So you multiply, I use a cross over here, right? The conjugate, well, that is equal to 2 plus 3i, that's multiplied by 1, and well, that is 2 squared and 3 squared, that is plus 9, that's equal to 2 plus 3i over 13, right? 1 over z, it's equal to z to the negative 1 power, it's equal to 2 divided by 13 plus 3 divided by 13, I there. And really the remark, right? Well, let's read the remark. Many of the properties of the new real number, of the real number system R holds in the complex number system C, but there are some truly remarkable differences as well. For example, the concept of order in the real number system does not carry over to the complex number system. In other words, we cannot compare two complex numbers. That is z1 equal to, right? Sure, we can copy that. Remark. concept of order in real numbers does not carry over. Carry over to complex numbers, right? That is okay. Z1 is big, well, Z2 is bigger than Z1, or Z2 is bigger than or equal to Z1, have no meaning in complex numbers, right? That is one of the remark. And remark 2. No. Okay, so this is our first chapter. No, this first session of complex analysis, and I hope you guys enjoy it. And I will publish this video and the sequel of it, 1.2, soon. Okay.